everyone. Thanks for coming. So today I am going to talk about expression templates and the ways that we can use them to both specify and to compose units of DSP together. And importantly, it's a very compile time heavy idea. So all of what I'm just going to describe is with a compile time view of things in mind. So for those of you who don't know Sing, we're a small company, a startup, and we launched our first product this year, which is the Sing Cell Alpha. The Sing Cell Alpha is a loudspeaker with a particular focus on spatialization. So it has 8 drive units arranged into 3 waveguides, and the cell can either operate alone or in conjunction with others to create an immersive spatial representation of sound in the room. As you can imagine, a product like this has pretty specific DSP requirements, and so this talk is really geared towards one of the major tools that we've used at Sing to implement some of the DSP that we need. So before I get to the specifics of the DSP part, I just want to give a quick primer on expression templates themselves, because in talking to people, I get the impression that people find them to be a bit esoteric, a bit niche, a little bit scary maybe. And I want to dispel some of those myths. Expression templates are conceptually very straightforward. So here is my description of how they work. So let's say you're in the business of adding 2 stood vectors together. And you're a DSP person and you come from MATLAB and you want to be able to write syntax that's kind of MATLAB-like. So you want to be able to write x equals a plus b. And in C++, the way we'd do that, kind of naively, is we would implement operator plus, and we would do it such that it takes 2 stood vectors. And then in the function body, we would create a return object. We would iterate over our input, or inputs, and we'd add them together and we'd push back into our return object, and then we'd return it. And then in our main function, we could write something like this, right? We have 2 stood vectors defined, and we can write autoconst x equals a plus b. And this works great. X has the right values in it. Everything does exactly what we want. Now the problems start rising when we have a more complicated expression. So even just a plus b plus c is complicated enough to illustrate. We can write this using the same operator plus, and it's still correct in the sense that a still has the right values in it. But what we'll find is that we have called operator plus twice, and in so doing, we've allocated 2 return objects, one of which will just be thrown away, and we've traversed the for loop 2 complete times. So we have a kind of a performance loss if we do this, and this just gets worse and worse as the expression becomes more complicated. In addition, even if we could somehow, actually wait, excuse me. So what we would prefer really is if we could have maybe a 3-input operator plus, which obviously doesn't make sense. But let's say we could somehow do this. So it's going to take 3 stood vectors, and we're going to have 1 traversal of the for loop, and it's going to index it into all 3 inputs in 1 loop. So we kind of save the performance thing here again, right? We have 1 return object with 1 allocation. Ignore the fact that I'm pushing back and it's going to be allocating. Let's just pretend that that's not happening. But we have avoided the problems I just described by having this. But of course, this doesn't make sense because it's a 3-input operator plus, and this does not scale either. Like, you know, if you could somehow do this for a complex expression, then you've just written the whole expression by hand, and you haven't actually got the benefit of an operator anymore. So this doesn't work. So what is the alternative? Okay, the alternative is expression templates. So instead of going straight to a stood vector as the thing that we return from our operator, we instead are going to come up with a dedicated type that's just going to sit there and represent the sum. And I've called this type vec_sum, and this is a template. It takes a v1 and v2, and v1 and v2 can be anything, but they have to be vector-like objects, vector-like types. And what I mean by that is that they need to provide a subscript operator, and they need to provide a size method. And when we construct one of these, we give it instances of v1 and v2, and all it's going to do is it's going to take references to those things and save them into some reference member variables. Not going to do anything else. It's going to do no computation. It's not going to allocate anything. It's just going to sit there. And of course, this costs nothing to create, really. But it's going to sit there, and it's going to represent the sum of 2 vectors. And what we see is the magic happens when we index it into this object, right? So this provides a subscript operator, and if we ask it for its 5th element, it's going to reach into its inputs, and it's going to compute that for us on demand. Okay. And because this has a subscript operator and a size method, this is itself a vector-like object and could be further used as an argument to another vector. So finally, we implement our operator plus to return one of these. And so operator plus becomes something like this, where it takes a v1 and v2, and it just forwards them. And then finally, in our main function, we can have our 3 stood vectors. We can write a plus b plus c. And if we look at the type of x, if we look at the type of x, we'll see it looks like this, which is a vec sum of a vec sum of 2 stood vectors and a stood vector. So you can see that even with just this very simple expression, we're building up this big nested type, and that type is being generated by the expression template machinery, by the operator plus. And then if we actually want to reify this into a real container with real numbers in it, we can do so later. We can create a stood vector, and we can iterate over our expression object, pull numbers out of it, push them back into a vector. But this is independent of the creation of the expression, specification of the expression, and is something that we can do at a later time. Also importantly, if we even do this, there is only going to be one allocation, which is the stood vector of y. There's only one object that needs to be made, and we could even pre-allocate y if this is in a real-time context. So that could be allocated in a prepare method or something for a plugin. So this is preferable in many ways. So expression templates are an alternative to kind of greedy computation. They're computed on demand. The expression objects themselves do not allocate anything. So we can make these very large expressions, which do not require any internal allocations or have any performance, like real-time performance worries. And I haven't really mentioned this, but because we only have one single for loop, the compiler has many more opportunities to optimize the body of this for loop. So all of the full expression can be optimized jointly, which is not really the case when you have multiple for loops, each with one operation being done. So that's expression templates 101. And when I talk about expression templates, like this is what I mean. So we have an operator. It's going to return us a dedicated type, which represents that operation, but the computation will be done later. Okay. So this talk is about the expression and specification and composition of units of DSP. And it would be remiss of me not to mention the fact that we have one of those, and it is plugins. Now, plugins are excellent at what they do. They, of course, are super mature. They've had a ton of work thrown at them. And they really sort of satisfy their core design premise. And it begs the question, if you like plugins so much, then why not just use plugins? And the short answer is, I have used plugins for a long time. And in the kinds of work that I've needed to do, I have not found them to be a particularly good fit. And I'm going to explain what I mean by that. So plugins, to my mind, plugins are intended primarily for recording studio users. And this really begets 2 things. One is that they must be distributable. They must be kind of black boxes that you can buy from multiple vendors, and they must be generically hostable. So this means, I can buy plugins from a bunch of different people. I can load them up in my DAW and expect them to work together. Now, the way we achieve these 2 goals concretely is they must be a dynamically loadable module, and they must present a predefined interface, an API, right? This is the plugin definition. And that is what plugins do. And I would say both of these, the fact that it's a loadable module and that it's a predefined interface, both of these have implications in terms of how we have to design and build and work with plugins. So I'm going to treat both of these slightly separately, although they are connected. I would say the interface, being very geared towards recording studio use, it's very opinionated. It talks about channels and buses. It only allows floating point signals. We have parameters, so we can control how the DSP works, but these are really geared towards implementing knobs and sliders and things that you find in recording studio equipment, and this is also limited to floats under the hood. We have metering, that kind of piggybacks on top of parameters and is also limited to floats. And then we have MIDI, which I've never needed to use MIDI, but I've always had to talk about it when I make a plugin, because it's there in the interface and you have to deal with it. And then on the dynamically loadable module side, just making a module is not a trivial thing. There's code boilerplate, there's this large-ish interface you have to fill out, and there's project husbandry. You have header files, you have things you have to, details you have to fill out in order to make this work. Of course, Producer helps with this, but it's still a non-zero amount of effort that you have to put in and a non-zero amount of project husbandry you have to engage in. Now, if you construct a sort of large system out of plugins, you are unable to globally optimize that large system, right? Because the plugins are all precompiled and you can't do any kind of global optimization of the final system. And furthermore, function calls into each plugin are expensive, and you do not want to be doing it 48,000 times a second for each plugin. So to ameliorate that slightly, we use block-based processing, which is a mainstay of computer-based audio. But even using block-based processing, there is a lower limit on how granular you're really willing to allow your plugins to become. Because at some point that you're going to be spending more time in the plugin overhead than you are doing useful work. So plugins end up being quite coarsely defined. They end up being quite big. And if you want a finely granular system that you can compose together, plugins are kind of not best suited for that. The interface to a binary module is this quite limited C interface, right? Because that's just how they work. So you can't do anything interesting with types. All you can pass across the boundary is pods and pointers, more or less. And finally, working with plugins is a little awkward, especially if you're working in an embedded kind of environment. You have to make sure that if you build your plugin, you have to sync it to the device. If there's presets or graph files, you have to make sure those match and they're the right versions. And there's more friction, there's more things for me to forget, and I frequently do. And I just find this to be kind of just friction in the development process. And finally, I will talk about block-based processing. I find it to be really awkward. In particular, it requires quite a natural, I would say, wrapping at code boundaries. So you have, the process function for plugins has to be given an output buffer to write into. And as a functional programmer, I find that borderline offensive. In general, things that deal with blocks in an environment where you cannot allocate blocks in real time require awkwardly shaped functions. Furthermore, we often find ourselves pressured into using SIMD intrinsics, which obviously eke the very most performance out of everything. But if you've ever had to stare at code that looks like this, then I sympathize. This is not a direction I think humanity should be going. This is not fun. And finally, and this may not affect everybody, but the composition infrastructure for block-based processing is not trivial. Because if you have a plugin host, it needs to deal with buffers, needs to allocate buffers, figure out how many buffers are needed, how to share them around so they don't clobber each other, things like that. And if you have to maintain a host like that, that can be an ongoing source of significant maintenance work. So plugins have in many ways become the hammer that you reach for when you see this nail of I need componentized DSP. But my question to myself was, I have been bitten by all of these kind of downsides over the years that I've been using plugins. And in the specific case where you don't need the flexibility that plugins provide, which is, in my case, the embedded use case where you're building a product and you have full control over the kinds of DSP that's in the product, could this development case be better served by something else? So I was casting around for ideas, and I came across this ADC talk by Ian Hobson from 2016. And in this talk, he was talking about compile time signal chains. And in many ways, he had similar goals to me. So he was thinking about, can we do something interesting for signal processing purely in C++, using kind of concept machinery and things like that. And while I will say we did go in quite different directions in terms of the code that we both came up with, the beginning of his talk gave a really good description of Faust and Faust's composition algebra and the way that works. And as soon as I heard it, I was immediately taken with this. I wasn't really familiar with Faust at the time. As soon as I heard this, I was immediately convinced that this is the right way to do DSP composition. And as a kind of template metaprogramming fan in C++, I also immediately had an intuition that it would map quite well to the way that Faust does the composition. So I was on with this and sort of excited to try it out. And for those of you who aren't Faust people, I'll just give a very, very quick overview of what I think Faust is and why Faust is great, but also why I'm not using it. So Faust is an embedded DSL, and it's designed for the expression and composition of DSP, so it really fits my brief in many ways. In terms of the way you use it, it transpiles to C or something else, so you can build it with an ordinary C compiler. The language is sample-wise, so there's no horrible blocks to deal with. And the composition overhead is very low, so you can make very granular statements in Faust and not worry that you're going to be burning time in the composition part. Now, Faust does have some downsides. It's a DSL, so there's an additional tool. You have to hook it into your build system, and there's complexities around that. You don't have access to the C++ type system. Obviously, you're in a different language. And I will kind of elaborate on what I mean by that in the following slides. But suffice to say that when you're in a DSL, you're limited to the features of that DSL, and if there's something that you needed to do that it can't do, you really can't work around it. Right? The feature has to be there in the DSL. Whereas if you're in C++, you often will be able to kind of make something work yourself. And finally, with the DSL, there's a border around the code in the DSL, and if you have fussy requirements about how you need to interact with the insides of what's going on in the DSL, it can be difficult to meet those needs depending on what they are. But Faust has this composition algebra. And what I mean by that is it provides these binary composition operators. And specifically, series, parallel, split, feedback, and join. I will say I have not needed join, and I don't really get join, but I've needed the other four, and I will describe those, and I've implemented those. And as a brief rundown, these operators look a bit like this. So if we're putting A in series with B, we're going to connect all of A's outputs to all of B's inputs. And a strict requirement of Faust's composition is that the composition must be complete. You can't have any dangling inputs left over. So there must be exactly 3 outputs and exactly 3 inputs, and nothing left over. That's the rule. Parallel composition just puts A next to B. So you just concatenate the inputs and outputs, and that's your new kind of unit. And then split is a little bit like series, except the C in this case can have more inputs than A has outputs. It needs to have an exact integer multiple of A's outputs, but if it meets that requirement, then we will cycle through A's outputs, so it will be like 1, 2, 3, 1, 2, 3, 1, 2, 3 for as many copies as it has. And then feedback, I do apologize, my little SVG plotter doesn't know how to draw feedback composition yet. So imagine, if you will, you've got A and B next to each other, and B is in a feedback loop around A. So B's inputs are all connected to A's first outputs, and then B's outputs are connected to A's first inputs. And it inserts a sample delay in the loop to make it causal. Okay, so this is how Faust does composition, and I was interested to see if we could mirror this with C++ kind of TMP and get something that's purely within C++ but has the advantages of Faust. That was my goal. And with all this in mind, I just sat down and started writing some code. So the simplest unit I could think of at the time was an adder, 2-input adder. I'm just going to add like 2 channels together or something like that. And so I just wrote a struct, it does nothing. The first thing that we have to describe is the inputs and the outputs. And so to do this, I knew that I wanted to be able to support arbitrary types, so not just floats, as we get in many other systems, including Faust, but I knew I wanted my units to be able to take inputs and outputs of any types. And anytime I need to write a list of types, I reach for std tuple, because it's just the most natural thing. So I've defined two tuples here, and 2 type aliases, ints and outs. And these are useful because they will take any types, and also this is visible from outside. So when it comes time to compose things together, the ints and outs type aliases will be visible to that machinery. And then we add a process function. And process is just going to take an instance of imps, so it's going to take an actual std tuple value, runtime value, with 2 floats in it. And I'm going to do std get, and I'm going to add them together, and I'm going to wrap the result in a new tuple, which is an instance of outs, and I'm going to return it. So that's pretty basic. Because I like it, we can also make it const expr. Because why not? There's nothing in the way of that, and I generally will make things const expr if I can. And then, we've got the type system now, so we can do some interesting stuff. So we can make this a little bit fancy. We can make it a template. Instead of taking 2 floats and outputting a float, it can now take 2 t's and output a t. So this now works for doubles and ints and whatever you want to use it with. And we can even make it extra fancy by making it take a t and a u and then figuring out with decal type what the output type should be. So you could add, a float and a double, and the output type is going to be double because that's how operator plus works. And this will really work for anything, any T and U pair for which operator plus is defined. So that's kind of nice. I wanted to include an example that had a non-audio type input, so I just thought I would throw in a selector. So this has two T inputs, but also a bool input. And based on the value of the bool, it's going to select either the first T or the second T and pass that to the output. Compile time constant. These are often something that we want to have kicking around in our graphs. So this is a dedicated box. It has no inputs, but when you call process, it's gonna output a value, and it's gonna be a compile time constant value. Now this would be much neater if the non-type template parameters feature of C++20 was more widely implemented, but it's not present in my compiler, so I am having to lean on a slightly older style of this. So we're gonna have to provide a little struct as our template argument, which is gonna have a value member, which is gonna describe the actual compile time constant value that we want. But we will put this all together like this, make constant of 5, and we can choose the type we want it to be. And so when you call process on this guy, it's going to give you a tuple with one int in it of value 5. And then finally, in our grab bag of random things I implemented, we have the identity. And all this does is it forwards its input to its output. And to anyone who's not a Faust user, this looks completely useless, but I promise it's actually indispensable. And the reason it's indispensable is, let's say we wanted to make a little add 5 type box using our adder, right? So we're going to connect a 5 constant to the first input of the adder and leave one input exposed. So anything you give to the input will have 5 added to it. You can't do this with the series composition because the 5 constant only has one output and adder has 2 inputs. So the way that you do this is you put the 5 constant in parallel with an identity, and then you put that composition in series with an adder. So the identity box is used all over the place in Faust, and also I've used it all over the place in my stuff here. Okay, so now we've seen how we implement individual units of DSP. Now how are we going to connect them to each other? So I'm calling these units kernels, and so K1 and K2 is kernel 1, kernel 2. We're going to put K1 and K2 in series with each other. This is going to be another struct. We need to define the inputs and outputs. Well, that's super easy for series because the inputs are going to be K1's inputs and the outputs are going to be K2's outputs. And further to that, we can actually add a little static assert in here, asserting that K1's outputs are equal to K2's inputs because they have to be the same or series doesn't make sense. So that's kind of nice. If you try and compose two things that don't work, you'll get at least something resembling a nice compile error message. It would be nice if we could customize the string, but it still has to be a literal as far as I know. And then we have the process function. And also note that we have actual instances of K1 and K2. So when you construct one of these, it's going to default construct K1 and K2. And then when you call process, it's going to call into them. And for series composition, we're doing like literally function composition. So we're doing like g of f of x, right? So in this case, it's K2.process of K1.process of x. And that's it. That is the series operator. That's how series composition will work with the kinds of units that I've described. It's actually pretty simple. And then to come full circle, we implement the actual C++ operators that are going to invoke this stuff. And I have the series one at the top. We couldn't use Faust's actual literal operators because C++ doesn't let you do that. So I've chosen kind of ones that I thought made some degree of sense. So I've chosen, the stream input operator for series because it kind of goes left to right, and that's what that looks like to me. I've used the vertical bar for parallel, the less than sign for split, and then the hat or the caret for feedback. And then you can just assume that I've implemented parallel and split and feedback classes kind of similar to how I did the series one. They're a bit more complicated, but if you follow the series, then you'll figure out how to do those. And then how do we use this in practice? So let's say we have all of these primitives that I've just defined, and we want to make a 4-input adder. And so the diagram on the right is really what we're aiming for. And the way we express this is the thing on the left. So we make a type alias, we give it a name that we like, and we open a decal type, and we start creating instances of stuff and using operators. And we find that the 4-input adder has this as the type. This is just what comes out of the operators. So it's a series of a parallel of 2 adders and another adder, which is exactly what we see in the diagram. And then to actually use this to process numbers, all we do is create an instance of it. So in our main function, we take our new type. I mean, it's a template, so we give it a template argument, create an instance, and then we call the adder.process. We give it a tuple with 4 integers, and it gives us back a tuple with 10, which is exactly what we hope it would do. Also note that because all of the pieces are declared const expr, this result is actually computed at compile time and is const expr too. So that's actually kind of neat. That just comes for free. I would say that this slide kind of embodies the real crux of my talk. So we've seen how to both specify individual units and the basic mechanics of how we compose them together, what the syntax looks like. And the thing at the top left is really what using this type of thing looks like, at least when I do it. So you make these little compositions, you define new types or type aliases, and then you can instantiate them and process with them. Now we're in C++ and we have all this magical template machinery that we can use. Let's say we wanted to make an n input adder, just as a fun exercise. So if we think about this problem, it decomposes recursively. So let's say n is even. What we need is a pair of n over 2 input adders in parallel, followed by a 2 input adder. And if n is odd, we need an n minus 1 input adder, which is going to be even, followed by another adder, and we just take that extra input and we route it to the end and add it in at the end. So those are the two cases. And the way we implement this, or the way that I've implemented this, and this looks like a lot of code, but it really isn't, I have a function called n input adder helper, inspired name. It takes 2 template arguments, n and t. So n is the number of inputs you want, and t is the data type. And then there are 3 overloads, and they're each guarded by an enable if. So we provide the sentinel case at the top, which is when n is 2, and that just returns a regular adder, because that's a primitive that's already done. Now, if n is greater than 2 and is odd, then we do the thing that I just said. We make an n minus 1 input adder. We recursively call this function again with n minus 1, put that in parallel with an identity, and then put that in series with an adder. And if n is greater than 2 and is even, we make a pair of n over 2 input adders in parallel and put them in series with an adder. And then finally, we hide all this away in some namespace somewhere, and we define this little helper type alias called n input adder. And that just takes n and t, and it calls this function inside a decal type and gets the final type. And this is kind of all you really see as a user. You'll use this guy. And if we start exercising this for 4, we see that we get the thing that I had, which I did by hand, 4 input adder. If we do it with 5, we see this. If we do it with 6, and 7, and 8. So we've gone through, between 2 whole powers of 2, and you've seen all the different permutations of the extra things that happen. And then just for completeness, 32, just so you can see that this thing will just keep scaling. And finally, the thing that I like actually probably the most about all of this is when everything is const expr, you can unit test your code with static assets. And I do this all over the place. Like this is transformative for me. So I've made this little machine, this n input adder template. And in these static asserts, I'm making a 4 input adder, calling process with 4 ones, and I'm asserting that it gives me back a tuple with 4. And this is done at compile time. And I just litter my code with these now. And it just works really well. These just quietly sit there and make sure that you haven't broken any of your template machinery if you make a change. So all of this up until now has been stateless, right? These adders are just pure functional things. And the good news about state is actually that it takes care of itself. You don't need to do anything interesting to have units of DSP that have state in them. By way of an example, we have a slew limiter, and this has 2 inputs. One is a slew rate limit input in units per sample, and the other one is just a signal, and the idea is that the output is going to follow the input subject to a slew rate limit. And I'm not even going to bother going into how the function actually works. Suffice to say that it has a member variable down here called mprevout, and you can just use it from inside process. You can update it, you can read it, and none of the composition machinery is going to care that you have this. This will just work. Now, the big thing is parameters. So all of this has been parameter free. How do we do parameters? And this was not immediately obvious to me. I actually had to sit and think about this for a while. I ended up going with something that was inspired by the constant box. So if you remember from a few slides back, constant is a dedicated kernel. It has no inputs. And the properties of the parameter in this case are described by a template argument. So we're going to give it a little struct that's going to say, in the case of the parameter, it's going to say, default value, min value, max value, what's your type. It's going to describe the parameter. When you call process on a parameter, it's going to return the current value of the member variable. And this is going to provide some additional API surface. It's going to provide set and get methods for the parameter's value. Now, the overall idea with parameters that I kind of ended up on is that when a kernel has parameters, you can access them like this. So if you have a list of the parameters, you can set parameter index 3 like this, and you can get parameter index 3 like this. And the parameter index is a template argument, and the reason for that is that parameters can be any type. So like get parameter will return a different type depending on which parameter you actually ask for. So it needs to be a template argument that you call it with. In this case, we're assuming that parameter 3 is a float. So the param kernel itself looks a little bit like this. So it, again, like constant, it takes the template argument, which you're calling P. It's going to inherit a type member from that, which is just P type. We're going to define inputs and outputs. There are no inputs. And there's one output of type type. And this is the kind of main change. We're adding an additional tuple next to ints and outs. So this is an additional thing. It's called params. And it's just going to contain P. It's going to be a tuple with one thing in it, which is the type P. And we are only going to concretely define a params tuple for the param box and for nothing else. And the way that works will become clear in a minute. Then at the bottom, we have a pretty ordinary process function. It's just going to return the current value of m value. And note that we have a member variable of type, which is going to have been initialized to P's default value. And then finally, we add the set parameter and get parameter methods. They take this I, the index. Get parameter just returns the value by constref. And set parameter will update the value of m value with what you give it. And I have a little thing here. I don't even know if I like it that much, but if the type of the parameter is an arithmetic type, we then have this little validate function that's going to at least clip it between P's min value and max value. But if the parameter is some weird other type, then it's just going to pass it through. This works in practice pretty well. And then the type of template argument we will give to param might be this. If we have a gain parameter, so it's just going to have some fields, describes default value, min value, max value, and the type. And I've defined this to be a template too, which you don't have to, but this means that gain can be used as like a float or a double if you want. And we would instantiate it like this. And that would be a fully functioning parameter box that we can then compose with other things. So now I think we have all the pieces we need to define, let's say, a parametric gain processor. So we do have one thing left. So we want to define our gain in dBs, right? So we need a way of converting dBs to a linear multiplier. So we have a little extra helper kernel that's just going to convert, has one input, one output. The input's in dBs, the output is linear. And then we start composing. So we make our parametric gain. It's a new type alias. We take a param of type gain. We put that in series with a dB to then. And then we take that whole thing, put it in parallel with an identity. And then we take that whole thing and put it in series with a multiplier. And the diagram looks like this. And this is almost done in the sense that the diagram looks right. But at this point, even though the gain box there has a parameter, right, it is a parameter, when you compose it in series with something, the set parameter and get parameter methods are going to become inaccessible because they're buried inside the series composition. So we do need to update our operator. So we're going to take series from this is what we had before, and it's going to become this. And this looks a little bit scary, but I'll take you through it. So we add a params tuple, and that's just going to look at K1 and K2 and concatenate their parameters together. So if K1 or K2 have parameters, we're just going to end up with a joint list of all the parameters. So that's going to be the parameters that this series object possesses. We're then going to add get parameter, because that needs to plumb through to K1 and K2's get parameter methods. We have two overloads because depending on which index you're asking for, it might need to be routed to K1 or to K2. And then we have the same deal for set parameter. It just dispatches it to the right one of the two things. Okay, so at this point, our little parametric gain thing will work. And then if we wanted to get a little bit more adventurous and a bit more useful, we have a little low shelf filter. So we're going to define a quick biquad, and this is a biquad, so whatever. It's going to take two inputs, and the first input is going to be some coefficients. So this doesn't deal with generating coefficients. This just deals with the nuts and bolts of implementing coefficients. Biquad coefs, I won't show it, but it's just going to be a struct with some named fields, so like B0, B1, B2, and so on. And this thing implements a biquad, and has the delay lines and has the member variables. In addition, we'll design, or we'll specify a filter designer. So this is going to take three floats, or three teeth, which are going to be the filter cutoff, the Q, and the gain. So the filter parameter is going to go in here, and it's going to spit out biquad coefs. So this is just another building block. And at this point, then we can start stitching things together. And I would do this in two stages. So I'd first of all, the top one is start attaching parameters to that low shelf designer. So that we then have, I've called it a parametric low shelf designer. So this is a thing that's going to have three parameters. And also note that we've put the gain parameter through that db_lin up there. And then once we have that ready, then we can define the parametric low shelf, which is where we take this parametric designer and we connect it to the biquad. And we see this graph at the bottom. Looks pretty much exactly like you would think. I do apologize for the routing of this wire. This is a little bit confusing. My plotter isn't very smart about this, but this wire is going into the biquad at the end. Okay, so we're almost done. We almost have a functional system. The final thing is sample rate, and I've left sample rate till the end because it's the only part of this that I think is a little contentious. Now, the reason it's contentious is it's fixed to compile time. And before you kick me out, let me try to make my case. I did try quite hard to not have this, but it is the most natural fit for this type of framework. And the reason for that is that we currently do not have any sharing of runtime values between, through the various compositions or between objects. It's all done via the type system. And if we did start sharing values, things would be passed to the constructors of things. This would mean that every kernel would need to know about sample rate and would have to accept a sample rate value in its constructor. But I don't like that. The adder, I think, should not have to know about sample rate. It has no use for sample rate. And this is the beginning of how you get interface bloat, right? It's when you make things know about stuff that they don't need. So I elected to keep sample rate compile time. And the way we will use it is that it's going to be exposed as a template parameter by kernels that care about it. So that's not all of them, but some of them that do, like the filter designer, needs to know sample rate. It's going to be a template parameter, just like we've been using T to do the data type. Now, a practical solution in using this in the real world, while we typically aren't happy with being nailed down to a single sample rate at compile time, we often are okay with being nailed down to a list of sample rates at compile time. So maybe we need to support 4 or 8 discrete sample rates, and we're kind of happy with that. And so a way of kind of straddling both worlds here is to use std variant. So you construct your graph's type, and then at the very end, you make a std variant with a bunch of different instances of that type with different sample rates. And then at runtime, you can select one. And this kind of gets us sort of the best of both worlds. Compile time does not like this, and binary size also doesn't like this, but it's not crazy. We typically only need a handful of different sample rates, and I found it to be quite livable. So the changes we need to make, for example, to the low shelf designer, it would go from this to this, where it takes an extra template argument. We add a little using fs type alias in here, so it's gonna actually have an fs member. And then in the process function, you can use fs : value to get the actual number. And so you can use this in the calculation. And then we need to make an additional update to our operators, but this one's easy. It's just one extra line. And I have this little helper type here that I won't show the code for, but it has some rules about how sample rates between kernels will compose. So if K1 and K2 both care about sample rate, they need to match. Right? We can't compose units that want different sample rates because that doesn't make sense. If only one of them care, then we take that sample rate and that becomes our sample rate. And if neither of them care about sample rate, then we don't care about sample rate. That's the kind of semantics around this. And then you'll define a list of valid sample rates, and these aren't special, these are just full types with a value member. And then we can finish the definition of our parametric low-shelf filter. So like the edits that we made before, we now show these up in the composition, so we'd have an extra template argument. That FS gets passed through to the designer. And then for the filter itself, we have this FS argument that gets passed through to the parametric designer. And then we can use it listed variant like this, if we want to do that. So this describes kind of the basics of all of it. I think this is working reasonably well. This has implications and things that you might not necessarily immediately think of, but one of them that I really like is the fact that parameter smoothing is so natural in this world. So it comes almost for free. And the reason is that once a parameter value leaves the param kernel, it's just signal at this point, and you can process it with any of the DSP that you would apply to actual signals. Oh yeah. And because of this, because it's being processed by a real DSP, there's no out-of-band mechanism for smoothing parameters. Every sample is guaranteed to be correct. This thing just runs. It's just like a flood of data, and there's no synchronization. There's no worrying about block sizes. This just works. And so if we wanted to take our parametric gain processor and smooth the gain parameter, we would do the following. So in addition to the slew limiter that I showed you earlier, we need a little slew converter. And all this does is it converts units per second into units per sample, because the slew rate limiter needed that. So we have this guy, it just divides by sample rate. And then we start making some compositions. So we are going to connect the slew converter to the slew limiter to make a slew limiter that takes its input in units per second. We are then going to make a slew limiter second with a compile time rate, because I, in this example, want a compile time like slew rate limit. So we're connecting a constant to this slew limiter seconds. We're then going to define a little helper struct which defines the rate as a compile time constant. And then finally, we're going to make a smoothed gain value, which just takes all of that stuff above, connects the gain smooth rate struct into it, and then puts it in series with the dB to lin. So these small series of compositions slowly build up towards something actually quite meaningful. And then at the end, we start connecting these things together. We have a smooth gain param, which is just what we just defined with a parameter connected to it, so we can actually treat it like a parameter. And then finally, we put that in series with a multiplier. And we have this graph. And again, I apologize for this wire. This looks like it goes in here, but it doesn't. It goes down here. But you can see the operation of all this. Okay. So the summary so far is, I think this thing has many positive properties. It's very like Faust. It's a declarative syntax. And if you're into that, which I am, then this is a very natural way to think about composing DSP. It's very, very type safe. Every input and output is a type, and the composition operators all care about types and will ensure at compile time that they fit. We have full engagement with the C++ type system, and we can automate the generation of structurally interesting things. And I find this to be very valuable. The sort of incremental type alias approach that I was just showing, where we just do a little bit of composition in multiple steps, yields extremely reusable components. And I know we all like to think that we write reusable code, but in truth, I don't think we really do that often. And I've been really struck by how reusable these components have been. And I've just been able to amass over time a pile of completely independent little units. And then every time I sit down to a new project, I have this big library available, and it's working really well. I also find that DSP using this is very fast to write. And the gap between prototype and production is actually very small. So I have a couple of times I've sat down and made a prototype of something, and then I've looked at it at the end and been like, I could actually ship this, because there's really no other way to express what I'm doing. And so I very much like this. It just it's a very safe environment. If it compiles, it has always just worked. And that's something that functional programmers talk about a lot. But I found it to be very true with this, and it's because we're leaning so heavily on the compiler and the type safety of everything. Now, it does have some negative properties. OO programmers don't like it. And if you work in a team with other programmers, that actually matters. So, it's if you have a team of people who like Faust, for example, then maybe this type of thing will go down well. But not everyone thinks this way, and so not everyone is going to be super into it. Compile times aren't great. They're fine. They're workable, but they are much longer than you would expect from equivalent amount of signal processing. Let's say. It makes sense. There's a ton of template machinery being invoked, but still, compile times are quite bad. Binary sizes also aren't ideal. I think this is partly due to me not knowing what I'm doing, but I suspect there's always going to be some penalty that you have to pay with binary size when you have this much templating going on. Okay. And then we come to performance, which at this point in the journey, and this is definitely a journey, is neither a good thing nor a bad thing. And I know that I kind of bigged up the performance possibilities at the beginning, and there definitely are some, and it does have some performance positive characteristics. Global optimization of the graph does happen. And I've proven this out a few times using Compiler Explorer. You can put things in and just see kind of what the assembly looks like. And I've gotten good results from this in many cases, but not all cases. In addition, something that I didn't really expect is that if you have a region of your graph that is const expa, then the compiler will see that and will basically write the output of that into the binary. Like that bit of the graph will collapse away. And all of the abstractions, all of the tuple stuff, definitely all collapses away. So in many ways, this works exactly the way that I would hope that it would work. But with that said, with more complex compositions, I've definitely seen cases in Compiler Explorer where it fails, the optimizer fails to see that it could actually do something really, really small, and you get quite a lot of execution that you would think you didn't need. So I would love if any of you are optimizer experts to please reach out to me, because I would love to learn if there are ways of engaging with the optimizer a little bit better and trying to convince it to do certain things. Now, we do have one fundamental problem, though, which is that if there's a part of the graph which is not const expa, but that we as designers know is steady state, it's going to recompute that every sample. So let's say you have parameter smoothing. When you update a parameter, it's going to be smoothing over time, and that's fine. That's going to cost some DSP, but it's eventually going to settle somewhere. But you're going to keep smoothing it, and there's no way to really specify that, like, this is done now. Please stop processing this piece of the graph because it's going to give me the same output every time. And so we have to reach in explicitly and do something about this. So I came up with a little adapter, and this really just serves as an example of the types of things that we can do if we apply some kind of subjective intelligence to how the graphs work. This is called settle latch, and this is designed to wrap a kernel, which we know as a designer, we know it's going to settle eventually. So it's a kernel that's going to have some parameters, and when you change a parameter, the output is going to start changing, but eventually it's going to settle on something, and it's going to stay there. And if we know that, then we can use this. So settle latch wraps the kernel K, and we inherit all of our stuff from kernel K. This is trying to basically be kernel K. And we have a little Boolean thing down here called settled, which initializes to false. And then in our process function, we just ask, are we settled right now? And if we're not, we process like normal, and we get a new value. And we compare that value to what we got last time. And if it's the same as what we got last time, then we consider ourselves to be settled. We just say we are settled now, settled is true, and we return our value. And if we are settled, if we are settled, then we don't do any of that, and we just return. Like next time we come through here, if we're already settled, we just return the last output. So we bypass the processing. And this is actually pretty cheap, because no matter how big and complex your kernel K is, if you're already settled, the only cost of this is checking a single Boolean. Is it true or false? And you can skip all of it just based on that one check. So that's kind of nice. And then finally, in the set parameter method, we when somebody sets a parameter, we just unlatch, right? We say we're not settled anymore, and then we'll need to process until the thing settles again. And then finally, just to make this a little bit easier to use, we could introduce new operators because operators are really useful. And so I've added an extra one here. I've chosen the unary minus. And when you do this, this is going to actually wrap k in a settle latch. And so what we find is we have this graph for our parametric gain. We just change it to this. And now the gain parameter is now got a settle latch around it. And that is actually where I'm going to stop talking. There's a lot more stuff that I could have said, and performance alone would need a whole talk of its own, I think. So I had a bunch more plans of stuff I wanted to show, and I didn't get to it, but maybe in a future talk.
Just a quick question. Can you do multi-rate DSP with this?
Yes, that was one thing I wanted to talk about. So I actually promised that in the little summary for the frequency domain processing. You can, and I do, and I just didn't have room for it. But yes, basically you can make like the way that I have settle latch at the end is like a wrapper for a kernel. You can make another type of wrapper that's going to start buffering up input, and when it collects a full buffer, it will pass that to the kernel. And so if you have the kernel, which is a frequency domain thing that takes a std array or something in a frequency domain, you can do this. I did not get to describe it, but I do this.
Question. It looks very promising. I was wondering, it seems natural for the sample rate to be another parameter, and also for the parameters to be just more inputs. And I wonder if you explored that and maybe the
sample rate to be, you mean, oh, like a runtime parameter, like a algorithm parameter?
Like more inputs. And,
I'm sure you could do it that way. I think the difficulty is going to be routing that parameter around the graph and making sure it gets everywhere. Even with actual like parameters, I've had trouble with that, and it can become quite complicated. It might be possible, but I think it would be a routing challenge generally to make sure that that value gets to all of the kernels that need it.
And doesn't that seem to indicate that it's not really scalable for more like this routing system? It's a bit.
It might do. I think that's a kind of time will tell type question. I have been using this for quite a while in Sing, and implemented relatively sophisticated things with it. There may well be systems where it really doesn't map that well, of course. I don't have infinite experience with it, but it has worked really well for the things that I've tried it with so far. But yeah, I can't rule that out.
Okay, last one online question. Okay. Is it possible for you to share the slides on Discord?
Sure. Oh, actually, maybe. I use Reveal.js, and I don't actually know how to share a Reveal.js. If someone can assist me, then sure.